Hello, let us continue our discussion on microprocessors. Today part 5. So far we saw microprocessor, its importance in microcomputer, how to program a microprocessor, that is 8085 microprocessor, and some programming techniques that we saw. And in today's discussion we will concentrate on interfacing, memory and I/O devices. The basic job of microcomputer is to accept data from input devices like keyboard, analog to digital converter, and it has to take instructions or read instructions from memory and process the accepted data from input devices according to the instructions, and the produced results should be sent to output devices like LEDs, printers or video monitors. For doing all these things, processor needs to be interconnected to I/O devices. Our concentration will be on this part, how we interconnect I/O devices to microcomputer system. So today's objectives are: we define what is interfacing, list different interfacing devices, then we distinguish between memory mapped I/O and I/O mapped I/O. It is also called peripheral mapped I/O. Then we take some examples and we analyze a memory interfacing circuit. Then lastly we define port address of a given I/O device. First let us start with definition of interfacing. Interfacing, designing logic circuits, that is hardware, and writing instructions, this part is called software, to enable microprocessor to communicate with the peripherals is called interfacing. That is, I/O devices cannot be directly connected to the system bus of microcomputer. We need some intermediate circuit, logic circuit. That part of logic circuit or that hardware part is called interfacing device. And we also need to write some instructions into interfacing devices, special interfacing devices. They are called programmable interfacing devices. Next, and the logic circuits are called I/O ports or interfacing devices. The other name for interfacing devices is I/O ports too. Now let us see some of the most generally used interfacing devices. The very popular and required interfacing devices, tri-state devices. These tri-state devices have 3 states: logic 1, logic 0 and high impedance state. You know, logic 1 and logic 0 states are common for all digital circuits, but this tri-state device has extra state called high impedance state. When tri-state device is in this third state, that is high impedance state, it behaves as if it is disconnected from the rest of the circuit. A tri-state device, here a tri-state device has a third line called enable. That is, unless this enable pin is activated, this logic circuit won't work. it will be in high impedance state. If we want to make use of this logic circuit, whatever the logic circuit may be, this enable pin must be activated, then only it comes out of that high impedance state, and whatever the outputs that logical circuit produces will have either ones or zeros. That is, it behaves just like a normal logic circuit. One example here, let us see inverter, tri-state inverter, this one. You know, this part is an inverter, extra pin it is having is, extra line rather, is enable, and this type of inverter is called active high enabled inverter. That is, to enable this inverter we have to put logic 1 here for enabling this inverter. If we place 1 here, that is logic high, then this particular device works as normal inverter. That is, if you put 0 as input to this, 1 will be the output, and if you put 1 as input, you will get 0 as the output. And we can also have this tri-state device with active low enable inputs. In this particular case, this enable pin must go low to activate this device inverter. Now let us see the second important tri-state interfacing device. This is buffer. Buffer is a logic circuit that amplifies the current or power. It is used to increase the driving capability of the data bus and the address bus. You symbol, you know, without bubble after the triangle, this is for buffer, and it has third line, enable line. We can have either active high enable or active low enable. This is very important interfacing device. We know in 8085 microprocessor based microprocessor 8085 microprocessor based computer system, we have to demultiplex address data bus. Lower order address, that is A0 to A7, is multiplexed with data bus D0 to D7. To separate these, we need to copy the address available or that is placed by the microprocessor on these lines when ALE goes high. That must be copied into a latch, so that we can make use of that address later. So latch is also an important part of interfacing device, and these buffers generally carry they amplify the signal so that the signal strength is better. Next interfacing device is decoder, a logic circuit that identifies each combination of the input signals present at its input. It is commonly used device in interfacing I/O peripherals and memory. Examples are 2 to 4 decoder and 3 to 8 decoder. Next device is encoder, a logic circuit that provides the appropriate code for each input signal. These are commonly used with keyboards. Here you can see 823 encoder. It has 8 inputs. We can think of these connected to different keys. Only one key will be activated at a time, that is only one line will go low, and that particular line code is made available at the output of this encoder. For example, this 0 line goes low, the output of this encoder will be 0 0 0. This code corresponds to this 0 input key. Similarly, if you take this 1 line, if this goes low, then this encoder generates 001 code, and to activate this encoder since it has active low enable pin, this enable pin must go low, then only this will come out of the high impedance state, because it is also a tri-state device. Next, let us see the fifth interfacing device, latch. Here in its simplest form, a latch is a D flip-flop. A latch is used commonly to interface output devices. You know the job of this latch, as we were discussing earlier, when lower order address data multiplexed bus, when it is demultiplexed, we have to copy address into latches. So that is done by using octal latch, which has 8 latches similar to this as shown in this diagram. So from this data pin, data will be entered into this latch, it will be stored in the latch, and that will be stored in the latch when this enable pin is activated. That is, when this enable pin goes high, then only we can write data into this D latch. And these are common interfacing devices, and you can see these are hardwired devices, non-programmable. These are fixed, that is, the jobs of these devices are fixed, that is, the functions are fixed, we cannot alter them. There are other types of interfacing devices called programmable interfacing devices. With these, by writing some control word into their control register, we can alter the function of the circuit too. Let us see them. These are programmable interfacing devices. Hardwired interfacing devices are limited in their capabilities, as each device can perform one function, whereas in a programmable device, functions are determined through software instructions. We write some control words into control registers of these programmable interfacing devices to alter the functionality of these. Next, a programmable device can be viewed as multiple I/O devices, but also performs many other functions such as time delays, counting and interrupts. For each of these, separate programmable interfacing devices are available, and some of them are combined too. Let us see some of the examples for programmable interfacing devices. Here, first one, 8155 or 8156. This particular programmable interfacing device is used with IOs, and it also has timers. Of course, this has memory too. Normally it is used for IOs and timers. And next device, 8355, it has IOs, that is, it is used for IO interfacing. Next, 8279, popularly used keyboard display interface. By using this, we can connect hexa keyboard and 7-segment LED displays. And next one is 8255. This is popular peripheral interfacing device. It is actually a general purpose peripheral interfacing device, programmable interfacing device. And for this, we can connect as many as 3 different IO devices. Next, 8259, it is an programmable interrupt controller. Next device is 8257, it is DMA controller. Next device is 8251, it is communication interface. Like this, some more programmable interface devices are also available. Now let us see different types of IOs. That is how microprocessor identifies interfacing, that is IO devices. See here, the 8085 microprocessor identifies peripherals either as memory mapped IO or peripheral IO on the basis of their interfacing logic circuits. That is, microprocessor can identify input output device as if it is a memory location, because with memory microprocessor can write data into memory location or it can read data from the memory location, as it reads data from input device and writes data into output device. So, based on this, processor identifies given IO devices either as memory device or simple IO device. Let us see the differences between this memory mapped IO and peripheral mapped IO. This is the comparison of memory mapped IO and peripheral IO. First we see the characteristic on which we compare. The first, here we are comparing based on the device address used. In memory mapped IO, 16-bit address is used for identifying the IO device. If processor is using, if it is designed with peripheral IO, then only 8-bit address is used for identifying the IO device. The second one, what control signals are used? With memory mapped IO, memory read bar, memory write bar control signals are used. Actually, 8085 microprocessor won't generate memory read bar, memory write bar or IO read bar and IO write bar signals by itself. It provides only IO by memory bar signal and read bar signal and also write bar signal. By using these three control signals, we have to generate actual control signals: memory read bar, memory write bar, IO read bar and IO write bar. When we say memory read control signal, it means IO by memory bar signal status is 0, that is, that pin goes low. That means microprocessor is doing something with memory. So, though processor is communicating with IO device, it makes use of memory read bar signal and memory write bar signal as if it is communicating with memory signal. Whereas if the peripheral is identified in peripheral IO, then processor uses IO read bar signal and IO write bar signal. It means IO by memory bar signal will be high. And now let us see next comparison. What are the instructions available in memory mapped IO? All memory related instructions are used, such as this store accumulator STA, load accumulator LDA, stacks, move R to M, add M, subtract M, and accumulator M, etc. What we can observe here is, we can not only do data transfer, but we can also do some arithmetic operations, because we are using memory related instructions. Whereas in peripheral IO, we are using only two instructions, in and out. And next, data transfer. In memory mapped IO, data transfer will be between any register and IO, whereas in peripheral IO, the data transfer will be only between IO and the accumulator. Accumulator is normally called register A. So, the data transfer will be between accumulator and IO device. Next, maximum number of IOs possible. In memory mapped IO, the memory map, it is of 64 kilobytes, is shared between IOs and system memory. That is, there is no limit for IO devices that can be connected. No limit in the sense, maximum limit is here this 64K, we can connect any number of IOs within this limit. Whereas in peripheral IO, the IO map is independent of the memory map, that is 64 kilobytes or safely can be used with memory. Along with that, you see 256 input devices and 256 output devices can be connected. Next, execution speed. Speed here we are measuring in terms of T states. In memory mapped IO, 13 T states maximum are used with instructions like STA and LDA, and minimum 7 T states with instructions like move R to M. Whereas in peripheral IO, 10 T states are used, that is in instruction and out instruction they consume 10 T states. Next, hardware requirements. In memory mapped IO, more hardware is needed to decode 16-bit address, because IO device is identified with 16-bit address and it has to be decoded, hence more hardware is required. Whereas in peripheral IO, less hardware is needed to decode 8-bit address. And other features, arithmetic or logical operations can be directly performed with IO data. Whereas in peripheral IO, this facility, that is doing arithmetic operations or logical operations on data, is not available. Now let us take one example for memory interfacing device. We start it with studying one memory model. Here we can see model for this read write memory and read only memory. This is a memory chip. It has address lines and it has data lines called IO lines, that is through these lines we can send data or read data from memory with the memory. And along with this we are also having chip select. This CS stands for chip select, active low, hence it is chip select bar, read bar and write bar. Read bar and write bar, these are control signals. So if microprocessor wants to write some data into this read write memory, first it has to place address, that is called identification. Then it has to place data, whatever the data that it want to write onto the data lines, and after that it has to send write bar control signal, so that whatever the data available on the data lines will be copied into the desired memory location. And importantly, this chip select must be enabled. If this is enabled, then only we can do all these jobs. So normally what is done is a part of address is used to select the chip. And next, model for read only memory. Here it is very similar to read write memory, except write bar control signal. It has only, this is having only read bar control signal, because processor can only read from this, it cannot write into this particular memory. Next, this is little expansion of the previous one. This diagram describes memory chip. This is 2K memory chip, 2048 memory locations will be there inside it, each of 8-bit size. And for identifying these memory locations, address lines needed are 11, we will see it later, A0 to A10, they are connected to the chip, and internally they will be decoded. After decoding, a particular memory location will be identified or enabled based on the address present here. And input data, that is processor writes data into this read write memory through input buffer, and this input buffer must be enabled by using write bar signal. Anyway, this chip select must be activated, and when processor is reading, it must enable output buffer. And with read only memory, in this case EEPROM, we will have only read bar signal. Here you can see it is a 4K chip, hence 12 address lines are used. Now let us see the how memory register actually works, how it is constructed. Memory register has 8 flip-flops. Simplest flip-flop is D flip-flop. Normally D flip-flops are used, and let us study it. D flip-flop is like this. It takes data from this input and it must be enabled so that the data will be written into this, and that data will be available always at output. And this is the simple basic latch. And in the next figure we have the same latch with tri-state buffers, that is its input and output are controlled. Input is controlled with write bar signal and output is controlled with read bar signal. Processor, when it wants to write a bit into this particular latch, first by using address it enables this latch, and then it sends write bar signal, so that whatever the data available here will be stored in this latch. Similarly, when processor is reading data from this particular latch, it enables, that is identification, then it sends read bar signal, so that the data available in the latch that can be brought out through this tri-state buffer to the data line. And when these latches, normally these latches are connected in parallel to construct a 8-bit register. Now let us see a 4-bit register. We can expand that to 8-bit register. This is a 4-bit parallel in parallel out register. Here you can see the input data lines are controlled by this write bar signal. Write bar signal is connected to each and every input buffer. So putting all these buffers together, we call it input buffer. Input buffer is controlled by write bar signal. Similarly, output buffers, here you can see for each and every flip-flop, these are controlled by read bar signal. So putting all these output buffers together, we can call it output buffer, and we can extend this to 8 bits. Now this is the diagram for 4-bit register. Register is enabled by this pin enable, and input buffer is controlled with write bar signal, output buffer is controlled with write bar signal, and with a single block we show the control signals and enable pin like this. Next we see 8-bit register, actual 8-bit register. By using 4-bit registers, we can simply connect them in parallel as shown in this diagram. Write bar signal is connected to both, read bar signal is connected to both, and same A1, A0 pins are connected to both 4x4 registers. Now it becomes a 4x8 register. Here you can see by using 2 address lines, we can identify or we can enable any one of these 4 registers with the help of this decoder. And for writing, by enabling write bar signal, data can be loaded into that particular register, or we can read data from that particular register by enabling read bar signal. And now we see the same idea is extended for identifying 8 registers. In this particular diagram, to the right side of this, you can see for identifying 8 registers we need 3 address lines, that is 3 bits. So lower order bit is A0, next A1, and third bit A2 is used to identify the chip. Okay, and after inverting this, the same A2 is connected to next memory chip, M2 memory chip in this case. So as a result, what happens is we can identify 8 registers, 8 different registers. You can see in the left side diagram, if these 3 bits are 0 0 0, that is if 3 address lines are 0 0 0, R0 register will be identified like this. Lower order address bits 0 0, that will identify this R0 here, and first A2 bit is 0, so that will enable this first M1 group. And since it is inverted and applied to the second one. So, this the input to this chip select is, since it is high, this will not be selected or it is not enabled. So, like this we can, by increasing the number of address lines, we can identify more and more registers. Now, let us study this memory write cycle. Already we saw it. Microprocessor identifies the memory location by placing address in the first T1 T state, and it actually what we call it enables, or it make ALE signal will be made high, address latch enable signal will be made high, so that this lower order address data can be decoded and be used. And M bar signal is going low because it is memory related operation, and in the T2 state write bar signal goes low. So, by using this M bar and write bar signal, we actually generate this memory write bar signal. This memory write bar signal is actually connected to memory. When this goes low, the memory chip will place its contents or identified memory location contents on the data bus. This is how memory write operation is performed. Memory read operation is very similar to this. You see, in the first T state the particular memory location is identified, and in second T state memory read bar signal is activated with the help of IO by memory bar and read bar signal, and this memory read bar signal applied to memory chip, and in response to that memory will place the identified memory location contents onto the database. Next, how address is used for identifying a particular chip. It is, address can be decoded in two ways, by using direct multi-input NAND gate, or we can also use a decoder. For example, let us assume we have 4 address lines, and when these 4 address lines are high, the chip must be enabled, that is chip select pin must go low. So, simply we can use 4 input NAND gate here. Its output will be low if and only if all its inputs are high. Similarly, we can also use a decoder, 3-to-8 decoder in this case. Lower 3 bits are connected to the address pins of decoder, and that higher pin, that is A15, is connected to enable pin of this decoder. You see, this decoder actually having 3 enable pins, 2 active low enable pins and 1 active high enable pin. These 2 active low enable pins are grounded. So, this can be selected, this decoder can be enabled by using only 1 enable pin, that is E3 in this case. So, since A15 is high, this will be enabled, and since these 3 are also high, O7, that is output 7, will be activated. In this case it will go low, so that chip select becomes low and that particular chip will be selected. Now, let us take this simple 256 bytes of memory chip, how we interface it. Since its capacity is 256, it can store 256 bytes, that is it has 256 internal registers. To identify each and every register, we need to have 8 address lines. To calculate how many address lines are required to identify the particular memory location, we can follow this way. Here 256 registers are there. It can be written as 2 power 8 in terms of 2 powers. 2 power 8 we can, since it is 2 power 8 address lines are required, and as a result we can we can connect 8 lower order address lines directly to the chip, and remaining 8 higher order lines, they are used to select the chip. In this case those lines are used with multiple input NAND gate, and here you can see A15 to 8, these are connected through inverters to the NAND gate. So NAND gate inputs will be high if and only if all these bits are zeros, that is A15 to A8 must be 0, so that NAND gate has all high inputs. Then NAND gate output will be 0, hence chip select bar becomes 0, so this memory chip will be enabled. Now the memory map of this one can be derived this way. We write A0 to A15, and here we can see A8 to A15 lines are used for identifying the chip, and whereas lower order address lines, they can be, since they are connected directly to the memory chip, they can be varied from all zeros to all ones. So the address map will be 0 0 0 0 2, that is 4 nibbles are zeros. The last address will be 0 0 and FF. So the address map for this will be 0 0 0 H to 0 0 FFH. Let us see another diagram. In this case, this is very similar to the previous one, except A15 is connected to the NAND gate without inverter, directly it is connected, hence its memory map will change. Let us study it. Its memory map, for identifying its memory, see A15 now it has become 1, so its higher order nibble will be 8, and next nibble will be 0, next 0 0. So the first address of this for this chip, now it will become 8000, and last address 80FF, because the lower order address, that is from A0 to A7, the highest address possible is all ones, hence the memory map for this is 800 to 80FF. Now next take let us put these two things side by side and see. Here A15 is connected through inverter, here A15 is directly connected, hence addresses for the first one is 00002 00FF, and for the second one 8000H to 80FF. Now let us take one more example. Here this is 1K byte chip, here the address lines needed will be 10, because 2 power 10 is 1024. So A0 to A9, total 8 address lines are directly connected to chip, and remaining address lines A10 to A15 they are used to select the chip. Since all A10 to A15 they are connected through inverters, the address map will be like this: 00002 03FF. You can see this diagram again. Here this is the higher order address, this is lower order address. In higher order address, the very first up to 10, from A10 to A15 they are all zeros. So the higher order address will be 00002, lower order address will be, that is the last memory location, sorry, the address of last memory location will be 0, here 0011, that is 3, and all ones, that is FF. So its address will be 00002 03FF. Next, same thing can be done without using NAND gate. Here we are using decoder, 3 to 8 decoder, you see, and 01, that is one output of decoder is used to enable the chip, and since it is a 2 kilobyte chip, 11 address lines are needed, that is A0 to A10, and remaining address lines, that is from A11 to A15 are used for enabling this decoder as well as for selecting the particular output line. Here in this case A15 is 1, A14 must be 0, and for O1, for selecting O1 output, A13 should be 0, A12 should be 0, and A11 should be 1, so that this particular output line will be enabled, so that this particular memory chip, that is CE bar goes low, so this memory chip will be enabled. So the memory map will be like this: A15 is high, A14 is 0 to enable the chip, and 001 for enabling the output of the decoder, and remaining address lines, that is A10 to A0, they vary from all zeros to all ones. So this results in the address 8800H to 8FFFH. Now we connect 2732 EEPROM in the similar fashion. You can see decoder is used for enabling output, and 12 address lines are needed here for this memory chip, and remaining address lines A12 to A15 are used with decoder to enable the chip. Now this results in the memory map. This A15 must be 0, and A14, A13, A12 are zeros to enable output 0 line, so that it select the chip. So the address will be, the memory map in this case will start from 00002, here 0, this first nibble is 0, next nibble is F, and next nibble F, and last nibble is also F. So its address map will be 00002 0FFF as shown here. Next we see how the same chip, when particular address 0FFF is placed on the address bus, how it is identifying the memory location. By using the first nibble, all zeros, output goes slow, that is output 0 will go slow, enabling the memory chip, and next remaining 4 nibbles, all ones. Now the memory enabled or memory register selected or enabled will be this, and microprocessor can communicate with this by using read bar signal, because this is EEPROM. Now let us see I/O interfacing. This is very similar to memory interfacing, except in if I/O is identified as I/O device, that is peripheral mapped I/O, microprocessor will use only 8 address lines or 8-bit address to identify the I/O device. Let us see this block diagram of I/O interface. Here you see A0 to A7 address lines are used for generating a device or I/O address pulse, which in turn used along with control signal to generate I/O select signal. Our actual I/O device peripheral will be connected somewhere here, two peripherals, and the peripheral data lines are connected to the data bus of microprocessor through this latch or buffer. So to establish link between peripheral to data bus, we must enable this latch. This enabling is done by activating this I/O select signal, which in turn is generated with the help of appropriate address and control signal. Now let us take one example here. This is linear select decoding device with multiple addresses. Here processor places address, here only single address line, that is A0 is used. So when this A0 goes low and I/O write bar goes low, this AND gate output will become 1 and it enables the latch, so that whatever the data present here, that is microprocessor already places this data and then it activates control signal. So this data results or it activates the output device. In this particular case LEDs are used. So if you, for example, D7 line is made 0, and since it is connected to the cathode of this diode LED, and its anode is, since it is connected to VCC, so there is a potential difference and current flows through this LED and it glows. So for glowing this LED, 0 must be placed here. Next, and important thing is only one address line is used here, means for the addresses having even number like 0, 2, 4 and so on, for all those addresses this latch will be enabled. Normally we must select output device or input device with a single address, hence we must use all available address lines to select either input device or output device. Let us see this here. This is decode logic for dual inline package switch input port. So these are the switches connected to data bus through buffer, tri-state buffer. Here you can see when the switch is open, for example, you take this D0 switch, last switch, if this is open, VCC is connected to this particular line, hence D0 status will be high, that is 1. If the switch is closed, this VCC will be grounded through this resistor. So, the potential present at this D0 pin will be 0. So, if the switch is open, logic input will be 1, if it is closed, the logic input will be 0. So, that is the switch information. This must be read by the processor through the data bus. So, how to select this tri-state buffer? You see, as we saw in the previous block diagram, address A0 to A7 address pins are used along with the control signal IO read bar, and they are ANDed, they are odd here in fact, because bubbled input NAND gate is equivalent to OR gate. That is, when these two pins goes low, this IO select bar will go low, hence enabling the tri-state buffer. So, in this case, what will be the address of this IO device? You see, A0 to A7, all of them must be high, that is FF. Then only this NAND gate output will become 0. So, this particular input device address is FFH. Let us see another example. This is interfacing DIP switches. Now, for selecting this buffer, we are using decoder. Earlier we used NAND gate, here we are using decoder, that is the difference. But here too we are using A0 to A7 address lines, that is 8 bits only. Hence it is IO mapped IO, and we are using output 4 of the decoder. So, for enabling this, the input present to the decoder should be A2 must be 1, A1, A0 must be zeros. So, the address will be A7 should be high, A6 should be 0, A5 should be 0, and here you see A4 and A3 signals are not used. So, this also results in multiple addresses. Okay, if we assume those as don't care conditions, and if we give 0 value to them, so the first nibble will be 100, that is 8, 1000, that is 8, and the lower nibble will be 0100, that is 4. So, this particular IO device address will be 84. Next, this is memory mapped IO interfacing by using decoder, but here I am connecting input device, that is keyboards, as well as output device. Through output device I am controlling various appliances. So, if I send proper data, these appliances will be controlled through the solid state relays, that is the idea. And what is the address? Addresses are what are the addresses provided for this? For the first input device, you see the address is FF9. Here 16-bit address is used, that is, for identifying this particular input device or this output device, processor is using 16-bit address, unlike the previous case. So, processor is identifying these devices like memory locations, hence this is memory mapped IO interfacing. So, we can easily know it by observing two things. One is the control signals used are memory read bar, memory write bar, hence it must be memory map, that is one. And next, address lines used are A0 to A15, that is 16 address lines are used to identify this. So, it is a memory mapped IO interfacing. So, I hope you can analyze this. So, since input device is connected to O1, A0, A1, A2 must be zeros, and to enable this chip, E3 must be high and E2, E1 must become zeros. So, when these two will become 0 when all inputs are at low, that is A15 to when all inputs are high, because they are not inverted. So, A15 to here A4, they must be high, hence this forms address FF9. Similar logic can be applied for finding the address of this output device, it will be FF8. So far we have discussed definition of interfacing, listing of different interfacing devices, differences between memory mapped I/O and I/O mapped I/O, and analyzing a memory interfacing circuit. We saw some of the memory interfacing circuits with different addresses and finding port address for a given I/O device. In the next class we will see DMA, that is direct memory access, and some of the applications of microprocessor. Thank you.